Welcome to this explainer. Okay, so a lot of people look at science and just see this intimidating, impenetrable wall of math and jargon, right? But what if I told you it's actually the exact opposite? Today, we're diving into some source material that reveals science is, fundamentally, a beautifully simple way of filtering reality. It's not trying to make things complicated, it's all about creating a really clear, shared language so we can decode the world around us. Let's get right into it.
Section 1. Building simple models. Filtering reality.
The absolute very first step in scientific thinking, it's building mental models of everyday stuff. Let's kick things off with a highly relatable scenario pulled straight from our source text. Imagine you're hanging out, watching, or maybe playing a game of cricket, and bam, the batter just smashes the ball high up into the air. The immediate question on everyone's mind is, will that cricket ball cross the boundary for a six? If you actually want to figure that out, you've got to start thinking about what variables really matter.
Our source poses this exact question. Will the ball cross the boundary without hitting the ground first? Now, to answer this, we can't let ourselves get bogged down by every single atom in the universe, right? We have to build what the text calls a simple model. Basically, we have to filter out all the noise.
And that brings us to this idea of ruthless filtering. Think about it. The brand of the bat, the color of the ball, the exact amount of grass on the field, those things make absolutely no difference to whether that ball actually clears the boundary. Even stuff like air resistance and spin can kind of be ignored at first. Instead, we only keep the absolute essentials: the mass of the ball, its speed, and its direction. Boom. By isolating just what matters, we get clarity. And, as the text notes, we can totally add those minor details back in later if we want a more complex, accurate model.
The source applies this exact same logic to something we can all relate to: a simple bicycle ride home from school or work. If you're trying to model the time it's going to take you to get home, what are the details you keep? Probably just the distance and your average pedaling speed. What do you ignore? The color of your backpack or, counting the specific number of trees you pass. I really want you to realize that ignoring those details isn't being lazy. Not at all. It is a crucial, active technique for achieving scientific clarity.
And this brilliantly illustrates a much bigger point highlighted in the text. As we explore science more deeply, we apply this exact same filtering process to language itself. Just like we stripped away the color of the cricket ball, science strips away the ambiguity of everyday language, which leads us straight into our next crucial concept.
Section 2. The specific meaning of words. A shared vocabulary.
So this is where scientists take those everyday concepts we all casually toss around and assign them incredibly precise definitions. Words like force, work, or reaction. You might tell a friend you forced yourself to go to the gym, or you put a ton of work into a big project. But in science, our source emphasizes that these meanings have to be crystal clear and entirely unambiguous. Why? Because a scientist working in Tokyo literally needs to be able to describe their observations, compare results, and build ideas together with a scientist over in London. Without a strictly defined shared language, that whole global collaboration just completely falls apart.
Section 3. Symbols. The universal code. Now we're zooming out from specific words to an even more compact shorthand. If words are the foundation of this language, well, symbols are the highly efficient code written right on top of it. Really essential quantities are paired up with specific, universal symbols. Mass is just m, velocity is v, force is F, and electric current is I. By pairing these defined symbols with specific units, science basically bypasses language barriers altogether. It creates a genuinely global vocabulary.
But here's the cool part. These symbols aren't just convenient random abbreviations somebody drew out of a hat. A really fascinating question comes up. Why exactly is the speed of light denoted by the letter c? Well, the text explains that these scientific symbols are deeply rooted in history and long-standing international agreements.
As it turns out, the c, used for the speed of light, actually stands for the Latin word celeratus, which translates to speed or swiftness. I just love that. It's an incredible reminder that whenever we're reading a scientific formula, we're actually reading a rich, historical language that's been carefully curated over centuries of people working together worldwide.
And just to show you how staggeringly precise the shared historical code can get today, the speed of light, that historical c, is now a strictly defined physical constant. It is exactly 299,792,458 meters per second. No ambiguity, no estimating. Just pure, precise, shared understanding. Mind-blowing, right?
Section 4. Math is just a language.
All right, for a lot of folks, mathematics is the final and, let's be honest, often the most intimidating layer of science. But as we see clearly from our sources, that fear is based on a massive misconception. Now, the text acknowledges that, sure, using math can sometimes feel a bit challenging, but it firmly states that mathematics in science is absolutely not meant to be a hurdle. Instead, science turns to math simply to allow relationships between quantities to be expressed super clearly and tested carefully. It is literally just another dialect of our shared language.
In fact, the source text wonderfully redefines a word that strikes fear into the hearts of so many students: the equation. It says an equation is not just some robotic calculation tool. It is a compact statement about how certain things are related. Just think about that for a second. By reframing an equation from a scary math problem you have to solve into a simple logical sentence you can just read, it completely changes how you approach the whole subject.
And this really illustrates the incredible broad power of this language. With these simple, logical sentences, mathematical expressions can describe a staggering diversity of real-world phenomena. We're talking everything from the basic motion of distance and time to the invisible rates of chemical reactions, sweeping patterns of population growth, and even complex changes of energy within an entire system. It's all just sentences in the language of math.
So how do we actually put this into practice? Well, our source outlines a 3-step process that totally shifts the paradigm. Step 1, understand the situation first, just exactly like we did with the cricket ball earlier. Step 2, identify the relevant quantities. Figure out what details to keep and what to completely ignore. And Step 3, use mathematical relationships to reason carefully. Do you notice what's missing there? It doesn't say memorize a bunch of equations or blindly hunt around for a numerical answer. No way. It's entirely about reasoning and thinking logically. I want to leave you with this incredibly empowering quote pulled straight from our source. If you focus first on understanding the situation and the quantities involved, quote, equations will begin to feel less like obstacles and more like helpful guides in your exploration of science. Science really isn't trying to trick you. It's just offering you a map, a shared language, and a set of tools to filter reality. So my final question for you is this. Now that you know how to filter out the noise, what simple models will you start building today to decode the complex world around you?